Okay, good morning to everybody. Today we'll start with a new chapter of complex analysis, the calculus of residues, and it's related to complex integration. First of all, what's the zero of an analytic function? You must know about the zeros of a polynomial. We discussed it in our earlier classes. A zero of an analytic function fz is the value of z for which f of z is 0. Okay, for which the value we will get, the functional value will be 0. Suppose for an example, find out the zeros and discuss the nature of the singularities. Okay, first of all, we must know about the what is singularity. Okay, then we can find it. First of all, what is singular point? Okay, a point at which the function f of x is not analytic is known as singular point or singularity of a function. That means we must know that what is the singular point? The function who at a value which is not analytic. Okay, suppose for example the function 1 by z minus 2, that is the complex variable, has a singular point at z minus 2 equals to 0. That means z equals to 2. If z equals to 2, then it will be undefined. Okay, this is why it is called a singular point. And it is also singularity of the function. It is also called the singularity of a function. There are many types of singularity. We'll discuss this about today. Now find the zeros and discuss the nature of the singularities of this. F of z equals to z minus 2 divided by z square sine 1 by z minus 1. Okay, and this is the function, and this is the function of a complex variable. So poles of f of z are given by equating 0 the denominators. That means f of z, that means z equals to 0. Okay, here z square. Okay, denominator is z square. This is why we get as zeros using this. Is a pool of order 2. Order 2 means what? Power 2. This is why order 2. Okay, now zeros of f of z given by equating another denominators of f of z, that means z minus 2 into sine 1 by z minus 1. This is another function equals to 0. 0. So we have to consider from this product either this equals to 0 or sine 1 by z minus 1 equals to 0, because their multiplication is 0. So 0 multiply 0 equals to 0 is not possible. So either this equals to 0 or this equals to 0. This is why either z minus 2 equals to 0 or sine 1 by z minus 1. Then z equals to 2, and we get another one, z equals to, for trigonometric solution, we must know this formula 1 by angle equals to what? N pi. Okay, z equals to what will be just inverting on both sides, we get with this one for n equals to plus minus 1 plus minus 2 dot dot. So z equals to 2 is a simple 0. Z equals to 2, this 2 is the simple 0, and the limit point of the zeros are given by this. Okay, this is the series depending on different n, and z minus z equals to 1. Remember it, z equals to 1 for what? This. Hence z equals to 1 is an isolated essential singularity, because we got the simple 0 here, and we get another value depending on different values of z. We get and this z minus 1 depending on what? On sine. Okay, this is why z equals to 1 is an isolated from this product essential singularity. Now singular point what will be? This is the singularity. You must know. I have now what is the isolated singularity? Okay, if z equals to a is a singularity of f of z, and if there is no other singularity within a small circle surrounding the point z equals to a, then z equals to a is said to be an isolated singularity. Then if we draw a circle, if we get another point at outside the circle, then it will be isolated. Okay, it will be isolated singularity. So for example, the function 1 by z minus 1 into z minus 3 has two isolated singular points, namely z equals to 1 and z equals to 3. Because for z equals to 1, this will be undefined, and z equals to 3, it will be undefined. So z equals to 1 and 3 are the singular point. Another example of non-isolated singularity. Function, suppose this function 1 by sine pi by z is not analytic at the points where sine pi by z equals to 0. If this whole 0, then it will be undefined. Okay. So sine pi by z equals to what? 0. And after solving this trigonometric equation, we get pi by z equals to n pi. That means z equals to 1 by n. Pi pi cancel both sides. Depending on different n, we get different values of z. Okay. This equals to 0. So the singularity z equals to 0 is the non-isolated singularity of the function, because in the neighborhood of z equals to 0, there are infinite number of other singularities z equals to 1 by n. This is why non-isolated. And now pool of order m. Pool of order m. There are different methods for expansion of a function. Suppose there is a Taylor series, binomial series, exponential series. We must know about this in our earlier classes, especially in intermediate. So what is the Taylor theorem? Says in a complex function f of z, if a function f of z is analytic at all point inside the circle C, with its center at the point A, and radius r. Radius will be, the circle radius will be capital R. Then the each point z inside C, we get a series like this. F of z equals to f of A plus first derivative of f of z at A into z minus A plus second derivatives of f of z at A divided by factorial 2 z minus A whole square plus dot dot in this way. Nth derivative of f of z at A divided by factorial n into z minus a to the power n plus dot dot. Okay, there are a proof for this series, and I am not proving now because you have learned about it in our earlier classes. So this is the main series. You can note down in your copy. F of z equals to f of a plus first derivative of f of a z minus a, second derivative of a divided by factorial 2 z minus a whole square plus dot dot, nth derivative of f of z at a divided by factorial n z minus a. You must know if a equals to 0, then it will become Maclaurin series. Maclaurin series. If a equals to 0. Okay. Then it will become Maclaurin series. Here, if z equals to 0, then the series is called what? Maclaurin series. So we can make two corollary for that. If z equals to a plus a, then we can write this series. This is the another form of Taylor series. Remember it. So if a equals to 0, it will become what? Maclaurin series. Very very easier process for finding Maclaurin series from Taylor series. So we must we have to remember this about the Taylor series. Okay, now what is the actually Lorent? Another series look like a Taylor series, but it is the Lorent series. So first of all, what's the Laurent theorem? If you are required to expand f of z about the point where f of z is not analytic, then it is expanded by Laurent series and not by Taylor series. If it is not analytic, remember it. For analytic function, Taylor series, but for not analytic, f of z, and we have to use what? Laurent series. So in the statement will be, if f of z is analytic on C1 circle and C2 circle, suppose this is the C1 circle and smaller will be what? C2. And the annular region are bounded by two concentric circles C1 and C2. Concentric means what? Same center of two circles, C1 and C2. And radius will be R1 and R2, where R1 is greater than R2. We are observing from figure with center at A. Then for all z over this R, there are many values of z inside the circle C1 and C2. So f of z can be written as a0 plus a1 z minus a plus a2 into z minus a whole square plus dot dot b1 by z minus a plus b2 by z minus a whole square plus dot dot. We can define the f of z with this series. Okay, where an can be written as 1 by twice pi I c1 contour integration c1 f of w divided by w minus a to the power n plus 1 dw. That means this contour integration with respect to w. And bn, here bn is another coefficient. Bn can be defined by 1 by twice pi I, a contour integration of what? F of w divided by w minus a to the power minus n plus 1. Remember it, because bn is in z minus a is in numerator, sorry, in denominator, and here z minus a is the numerator. This is why n plus 1, and here in denominator this is why minus n plus 1. Remember it. So the C1 circle going anti-clockwise, that means it's positive direction. Okay, but C2 is negative direction. Remember it. Okay, so we can prove this by using Cauchy's integral formula. Cauchy's integral formula you must know, but I'm not proving now this. So this is the f of z. This whole series can be written as like this. This one. This whole series can be written as this series. F of z equals to n equals to 0 to n equals to infinity and z minus a to the power n plus n equals to 1 to n to infinity bn divided by z minus a to the power n. That means the whole series can be written as in terms of sum of two series. Okay, this is first series and this is the second series with this. Okay, this will become first series and this become second series. So it's the Laurent series also. It's called Laurent's theorem or Laurent's series. So now what will be the poles of order m? Now you must know from the series, from the Laurent series around z equals to a. Okay, if z equals to a, f of z equals to a naught, a1 z minus a2 plus z minus a, and this is the whole Laurent series. So in some cases it may happen the coefficient means what? This bm plus 1, bm plus 2, etc. will be 0. In some cases it may happen. So it's if this is equals to 0, then it reduces to the series can be written as like this. Okay, up to just bm. So greater than bm, that means bm plus 1, bm plus 2 will be 0. Then we get this one. So f of z a naught plus a1 z minus a2 z minus a whole square plus dot dot. We can take a common here 1 by z minus a to the power m. Then we have to multiply z minus a to the power m in each term. Okay. So then z equals to a is said to be a pool of order m. Order of m, because highest power what? M. This is why z equals to a is said to be a pool of order m. And the function f of z when m equals to 1, the pool of said to be a simple pool. So in this case, f of z equals to this. If the number of the terms negative power, then the this equation 1, expansion 1 is infinite. For what? If the number of terms of negative power, then z equals to a is said to be called essential singularity. Negative power. If there are negative power, then you get essential singularity. So we can now we can discuss some singularity. Now, what is the class? There are different types of classification of singularity. We have discussed it, and we have also isolated singularity. Different types of singularity we defined. Now, the essential singularity, we also defined this. And what will be the zeros of order m? We also defined this one. Now we'll discuss an example. What will be the we can discuss. Suppose this example. This is an important example for you. So discuss the nature of singularities of the following function. There are 5 types of function: sin z minus z, z cube, and suppose we are finding the singularities, nature of the singularities of the following functions. And first function f of z sin z minus z, z cube. And so 1 by z cube and sin z minus z can be written as like this. You must know sin z is a series. Sin x equals to what? X minus x cube by factorial 3 plus x to the power 5 by factorial 5 plus dot dot. You must know about this. Okay. Just 1 by z cube will be multiplied to each term. We get this series. So if we take limit z tends to 0, take limit of this function, then we get minus 1 by factorial 3, that means minus 1 by 6, which is finite. Okay. So if this is finite, then z equals to 0 is a removable singularity, or we can apply another one. Since there is no negative power of z, so z equals to 0 is a removable singularity. No power, no negative power. This is why z equals to 0 is called what? Removable singularity. So another second example, f of z is this. Poles of f of z is given by setting f of z equals to 0. If this whole equals to 0, we must know z square equals to 0 is undefined. So for finding the singularities, that we have to set z equals to 0, and this is the twice. Twice means what? Power 2. This is why z equals to 0 is a pool of order what? 2. And z equals to 1. They are another denominator. Z equals to 1. 1 by something equals 1 by 0 equals to what? Infinity. This is why setting this z equals to 1 is another singularity, and f of z is not defined at z equals to 1. Understand, everybody? So the zeros of f of z are given by what? Numerator of f of z equals to 0. Numerator will be this equals to 0, and either this equals to 0 or this equals to 0. So we have solved this in. So we get z equals to 1 is an isolated essential singularity. Now third one, f of z equals to e to the power 1 by z, z minus a whole square. So poles of f of z are given by what? Z minus a whole square equals to 0, and z equals to what? Twice a. So z z equals to a is a pole of order 2, because highest power what? 2. Now another zeros of f of z are given by what? This power e to the power 1 by z. So e to the power 1 by z equals to 0, and e to the power x form is a series. You must know e to the power x for series what? 1 plus x by x square by factorial 2, x cube by factorial 3, in this way. Okay. So we get this series, and there is no z in the complex number system which satisfies this. That means it's never be 0. For any values of z, e to the power something can never be 0. This is why f of z has no 0. Because if we take limit z tends to 0 of f of z, we get immediately infinity. That means infinite. The limit does not exist. This is why z equals to 0 is an essential singular point. Now another example like this, just denominator equals to 0 of f of z. Poles of f of z are given by z square plus 4 equals to 0. So z equals to, we get what? Plus minus twice I, and which are simple poles. This is the called simple poles. Now last example, z equals to 5. 5 of z equals to cot 5 z divided by z minus a whole cube equals to, we can write cot means what? Cos by sine. Okay, cos theta divided by sin theta. So poles of f of z are given by what? This denominator equals to 0. So either this equals to 0 or this equals to 0. So we get z equals to n and z equals to a. So z equals to a is a pool of order 3, because highest power what? 3. This is why order 3. And z equals to 0, plus minus 1, plus minus 2, all are simple poles. And this will be homework for you. Example 2 will be homework for you. Find the singularities of the following functions. This one, and this will be homework for you. Okay, and this is the result. So I hope you can do this example. Okay, now the definition of a residue at a pole. So let z equals to a is be a pool of order m, the function f of z, and c1 is the circle of radius r. This is the c1 first circle, smaller circle, radius of r, and with center at z equals to a, which does not contain any other singularities except z equals to a. Then f of z is analytic within the annular. This is called annular because this r is less than the distance between z and a. A is the center and z is the any values between what? Interior of the circle C1, and less than capital R. Capital R is the radius of bigger circle. So bigger circle, this there are many values of z. Okay, so distance between a center and this value different z, then z1, z2, z3, z2, z1. This point difference between many z and the center a, this distance will always greater than radius of the smaller circle and less than what? Big radius of the bigger circle. So it can be expanded within the annular Laurent series. Laurent series you must know, from Laurent series you must know about this. F of z equals to n equals to 0 to infinity and z minus I to the power n plus n equals to 1 to infinity bn z minus I to the power minus n. Remember it. This is so where n equals to what? This, and bn equals to 1 by twice pi I. N is the circle, whole circle C, and bn is the what? A smaller circle, f of z divided z minus I to the power minus n plus 1. So this circle z minus a absolute value, this distance will be equal to radius, being the circle C1, and particularly B1. If n equals to 1 here, we get B1. Okay, B1 equals to what will be 1 by twice pi I, n equals to 1, this will be 0. Something to the power 0 what? 1. This is why you get only fz, right? Z minus I to the power 0 for n equals to 1. Okay, z minus I to the power minus 1 plus 1, that means what? Z minus I to the power 0. So we get only this one. So B1 equals to 1 by twice pi I for the first circle, that means smaller circle, f of z dz, smaller circle. So the coefficient Bn is called residue of f of z at the pole z equals to a. Remember it. This is very important definition. What is the residue of a pole? What is the residue of a pole? This is the definition. The coefficient B1 is called the residue of f of z at the pole z equals to a, and it is denoted by the symbol residue of at z equals to a equals to B1. So this is the actually definition of residue, important definition. And residue at infinity. Infinity is z equals to infinity. Then residue will be infinity. So method of finding residues. Suppose residue at a simple pole. If f of z has a simple pole at z equals to a, then residues of f of a what will be? Limit z tends to a, z minus a into f of z. This is the formula for finding residue at simple pole. Suppose residue at a pool of order n, and this is another important formula for finding residue at a pool of order n. So residue, if f of z has a pool of order n, then z equals to at z equals to a, then residue at z equals to a equal to 1 by n minus 1 factorial and minus 1th differentiation of z minus I to the power n into f of z. We have to pick out this formula and write down the copy in copy. This is the residue at a pool of order n, and this is the residue at a simple pool. Just power will be 1, and here power will be what? N. Remember it. So using this this definition, we can solve different complex integration. And this is the residue formula. F of a equals to 1 by n minus 1 factorial, n minus 1 differentiation, z minus I to the power n, f of z. Okay. Now, this is the very important theorem for you, the residue theorem. If f of z is analytic in a closed curve C except at a finite number of poles within C. Suppose this is the anti-clockwise, that means in positive direction. There are many circles. Suppose C1, C2, C1 with radius with center A1, C2 with center A2, and C3 with center A3, C dot dot. Cn with center n. Then this closed integration f of z dz equals to twice pi I into sum of the residues at the poles within C. Within C, there are many residues, and you have to take the sum of these residues and multiply it with twice pi will give the total contour integration of f of z. Okay. Suppose let us consider C1, C2 dot dot up to C1 be n non-intersecting circles with center A1, A2 dot dot n respectively, and radius is so small that they lie entirely within the closed curve C. Okay, entirely closed curve C. Then f of z is analytic in this multiple connected region lying between the curve C and C1, C2 dot dot up to C1. So applying by Cauchy's theorem, you must know contour integration of f of z within the circle C equal to what will be contour integration of contour integration of the within the circle C1 plus contour integration of within the circle C2 plus contour integration within the circle of C3 plus dot dot up to nth circle contour integration of n circle. Okay, so you must know by Cauchy's integral theorem twice pi into residue of f of a. This is the what f of a1 and f of a2 and f of a3 into f of n. So just sum of the residues. So this is very important theorem, very easy theorem for you. And applying this theorem, we can solve many examples. Suppose there are examples using the residue theorem. Suppose this one, important example. Evaluate the contour integration dz divided by z square plus 4 whole square, where C is the circle, z minus I. This is the circle with radius 2, and center will be what? Center will be 0, 0, minus 1, 0, sorry, 0, 1. Center will be what? 0, 1. So this is the f of z function. What will be 1 by z square plus 4 whole square, and this can be written as what? Z square minus I minus 2i whole square. Okay, because I square equals to 1. So we get a plus b into m minus b formula, z plus 2i into z minus 2i, and square will be distributed. So z plus 2i whole square, z minus 2i whole square. So the poles of f of z are what? Z equals to minus 2i and plus 2i. Okay, and both poles are order 2 because highest power is 2. Now C is the circle this with radius with center what? 0, 1, with 0, 1, and radius will be what? 2. Because if we put x plus iy in replace of z, then equating real and imaginary part, what we can write? X square plus y minus 1 whole square root equals to what? 2 square. So we get easily center is this and radius will be 2. So putting z equals to twice I in this circle, twice I, we get what? Twice I minus I equals to I. This modulus will be what? This is a complex number, so modulus will be 1. Okay, and this 1 less than 2 because our circle radius is 2, so less than 2. That means it is inside the circle. Okay, z equals to twice I lies inside the circle C. So z minus I, another for z equals to minus twice I, putting this in the circle equation. So we get minus thrice I, and absolute modulus of this will be what? 3. Because modulus of z equals to what? Root over x square plus y square. That means root over real part whole square plus imaginary part whole square. So we get a real part 0 and imaginary part minus 3. So we get root over 0 square plus root 3 minus 3 whole square. So we get only 3. And this is the 3 greater than 2. So as z equals to minus twice I lies outside the circle because greater than. Understand? So we get actually z equals to minus twice I lies outside the circle C. So now we can easily observe the residue of twice I, which lies inside the circle, equals to 1 by n 1 by 2 minus n equals to 2. Okay, n minus 1 whole factorial to limit z tends to twice I. This will be n equals to what? 2. This is why in formula n minus 1 divided by z n minus 1. So n equals to the first derivative only, z minus twice I whole square f of z. So this z minus twice I whole square f of z equals to what? Given z minus twice I this 1 by this. So the limit z tends to twice I first this will be cancelled. We get z plus twice I whole square. Now differentiation of this what will be? 1 by x square formula what? Z plus twice I whole to the power minus 2. So x to the n formula what will be? N into x to the n minus 1. And dividing with the coefficient, multiplying with the coefficient of z. Z is 1. So we get only 2 divided by z plus twice I whole cube. Because z plus twice I to the power minus 2, we can write z plus twice I to the power minus 2. So z plus twice I to the power minus 2 minus 1 divide, okay, n into x to the n minus 1. Power rule, using power rule, we get the limit, putting the below of limit that tends to twice I. If that equals to twice I, we get 4I whole cube. So we get 1 by 32I. Now by Cauchy's residue theorem, this equals to twice pi r into what? Residue of twice I. Residue of twice I what? 1 by 32I. Putting these values, we get this result easily. Just using this residue formula, f of a equals to 1 by n minus 1 factorial dn minus 1 dz to the power n minus 1 z minus I to the power n f of z. Just putting n equals to 2 here. Okay, and taking the limits, we get the value of residue. Okay, now another example, similar example. Evaluate e to the power z dz z square plus pi square whole square, where c is the circle z modulus z equals to 4, where by using Cauchy's residue theorem. Now we are given this is the contour integration e to the power z square plus pi square whole square dz, complex integration. Let the function f of z will be e to the power z divided by z square plus pi square whole square. So the poles of f of z are given by, you must know, denominator equal to 0. Then z square plus pi square equals to 0 is twice. So z equals to plus minus pi I. So z equals to plus pi I and minus pi I are poles of order 2. Now we are test whether this pole or inside or outside of this circle. So if z equals to pi I, then putting in the equation of circle. Okay, z equals to pi I, then pi I lies between this modulus equals to what? Pi, and pi value what? 3.1416 dot dot. So we can write this is less than 4 because our radius of the circle what? 4. So this is inside the circle. Now minus pi I also inside the circle, remember it. So z equals to pi I and minus pi I lies inside the circle. So residues of pi I, z equals to pi I, using the same formula, 1 by n minus 1 factorial limit z tends to pi I d to the power n minus 1, then n minus 1 derivative formula, just putting n equals to 2 in that formula. Okay, so we get easily this one, just f of z equals to what? This one, and this will be cancelled. So e to the power z divided by z plus. Now we have to differentiate this with respect to z. Now Quotient rule, you have to use Quotient rule of derivatives. That means u by b square, b into ddx of u minus u into ddx of b. That means we get by using u by b rule, differentiating with respect to z, we get this one. Now after my, so then limit z tends to pi I will be this. One term will be cancelled. So this z plus pi I whole cube. So e to the power pi I, putting z equals to pi I in this term. Okay, we get this one. Now changing I to minus I, the okay, just you can use this whole. That means residues of minus pi I, what will be? Same procedure, just replacing I minus I. Okay, replacing I with minus I, we get residue of minus pi I. So just putting I equals to minus I by Cauchy's residue theorem, you must know this complex integration can be written as twice pi I into sum of the residues. Sum of the residues within and within the circle uh, at point z equals to pi I and minus pi I. So just taking sum, we get I divided by pi. Very easy result. Okay, and this is also important example. You can just first of all you have to find out the pools, then we have to test the whether it is inside or outside, because clearly the pole lie inside C. Z equals to 1 lies inside C and 2 also inside C. So just use the formula B formula. Okay, U by B rule, then we get the residue of 1 will be twice pi plus 1. Similarly, for another one, residue of 2 will be same. Okay, and by Cauchy's residue theorem, we get immediately this one. So now last example of this class, this one. We have to evaluate complex integration 12z minus 7 divided by z square minus 1 twice z plus 3 dz, where C is the circle. You must know this radius will be root over 3 and center will be what? 0 minus 1. Okay, so by using residue theorem, Cauchy's residue theorem, we can find the integral, value of the integral. Now this is given, and here f of z equals to this. We can find out the poles by setting the denominator equal to 0, either z square minus 1 equals to 0 or twice z plus 3 equals to 0. So we get z equals to plus minus 1 and z equals to minus 3 by 2. So z equals to minus 1, z equals to 1, and z equals to minus 3 by 2 are simple pole, individual values of z. Now we have to test whether whether these three values lies inside or outside the circle. So if z equals to minus 1, putting z equals to minus 1 in the given circle, z equals to minus 1, we get what? Minus 1 minus I. And modulus of this what will be? Real part whole square, root over real part whole square plus imaginary part whole square. So root over 2. You must know root over 2 is less than root over 3. That means this z equals to minus 1 lies inside the circle. And for z equals to 1, similarly root over 2 we get, and it is also inside the circle. Now z equals to minus 3 by 2, putting z equals to minus 3 by 2 in the circle equation. So we get root over 9 plus 4 divided by 1. That means root over 13 divided by 2. Then that means this is the outside the circle, because this is greater than the radius of the given circle. So we can decide it, z equals to minus 1 and 1 lie inside the C, and z equals to minus 3 by 2 lies outside the circle C. So first of all, residue of minus 1 will be just using the simple pool formula. Simple pool formula you must know. Which one? Simple pool formula. Just simple pool formula. This is the formula for nth pool. Okay. Simple pool formula. Okay. Limit z tends to a z to the power minus a f of z. Just using this formula, we can find this. Okay, we can find this one. So z plus 1 and f of z is given function. So after this, and we get this one. Now limit, just putting the limit values that equals to minus 1 here, we get 19 by 2. Similarly, residue of 1 will be what? Using the same formula for simple pool, residue formula for simple pool, limit z tends to 1, z minus 1, f of z will be this. So just putting z equals to 1 here, we get 1/2. So by Cauchy's residue theorem, you must know this contour integration will be twice pi into sum of the residues. Very easy example. So today actually we have learned this complex integration part, chapter Singularities and Residues theorem. We have defined singularities with classification and discussed the nature of singularities. of the function. As we discussed this, we have solved this these types of examples, and we have defined also the residue. Okay, what is the residue, and the state and proof Cauchy's residue theorem. We have proved this very small theorem, very easy theorem also, and show that this equals to 1 by pi and this equals to this. We have solved these types of problem. We also solved this, the last problem I have solved. And state Taylor's theorem or series and Lorent theorem or series. We have learned about these two series, very important series, Taylor series and Lorent's series. Okay, bye for today. Thank you. Best wishes for you.
Assalamualaikum, sir.
Waalaikumsalam.
Assalamualaikum, sir.
Waalaikumsalam.